Hi everyone, I'm Professor Tom Neal, and it is my honor to present to you John William Washa, who is in my Water Integrated Studies course. This course is all about probably the scariest course I teach, besides listening to the evil presentations, on what we're really doing to screw up water in our world. And so this semester, John and I have been working on one of the big problems of water, and that's its connection to energy and the creation of energy in the U.S. And he's going to tell you a good story about how we use water in fracking and in frac sand mining, and how we can possibly do it well. So, John William Washa.
Thank you. Good evening. Forgive me if I'm shaking off the chills from that last delightful presentation. So let's start. This past semester I had the privilege of being in Tom Neal's interdisciplinary 290 water study, and if I learned anything from it, I learned that water is connected to everything, especially in ways that we might not see. And so there are some obvious connections. Of course, we use it in food production, we use it to drink. I don't need to tell you guys that every living thing needs water. We use it for hygiene, or at least I hope you are. Industrial processes like agriculture, and especially hydraulic fracturing and frac sand mining. The last two are highly water intensive, maybe in a way that they're not really giving themselves enough credit for. They really require more water than even us human beings do. And so the question really is, what are the possible effects to water quality from hydraulic fracturing and frac sand mining? And really, how is hydraulic fracturing affecting our water quality? But moreover, are we willing to sacrifice water quality to maintain energy independence and supremacy? As you'll find out, we're going to do energy exploration. We're going to do hydraulic fracturing. So the real question is, how can we do it better, and what's going to happen? What are the ramifications if it's done incorrectly? So to give you a little bit of backstory, the graph on the left is an illustration of the world's ever-increasing consumption of natural resources, particularly natural gas that you can see in the green. Now, the U.S. Energy Information Administration has the United States as the number 2 producer and consumer of natural gas worldwide. They also have the United States as the number 1 total oil-producing country in the world, and the number 1 oil-consuming country in the world as well. And so what we are trying to figure out, or what we can see here, is that the United States is energy hungry. If you look at the pie graph on the right side of the screen, you'll see that the United States consumes more than 1/4 of the world's energy. That's more than 2/3 of what China and Russia use combined. And so, as I said, the United States is obviously energy hungry. We're searching for energy independence. And so how are we gaining ground in the international energy market? Well, through fracking. And fracking is big business because it's so lucrative and relevant. But what is fracking, or hydraulic fracturing? Well, it's really 2 technologies. The first one on the left there is hydraulic fracturing, which is the use of explosives and pressure to fracture highly dense, impermeable shale formations deep within the ground to allow special fluids to deliver a proppant, usually sand, which will hold the fractures open, making that shale permeable and porous enough to extract natural gas. Additionally, the technology of horizontal drilling is what made fracking cost effective. Now, by allowing one single above-ground well pad to produce multiple below-ground well sites, that allows us to maximize the underground shale profits, but minimize the above-ground surface impacts. And so, while hydraulic fracturing does not occur in Wisconsin, we have to ask ourselves, well, then who gives a damn? And the real question, who gives a damn, is Wisconsin gives a damn. And why? Because Wisconsin holds as much as 75% of the U.S. frac sand market. And now, this frac sand, as you can see, is it's a specialized quartz silica sand, and it's an integral part to making those really dense shale formations permeable and porous enough to extract the gas in the first place. And so if you can see in the picture that it's really uniform in size and shape, and what you won't be able to tell is that it's ultra durable. And so these frac sand operations, they use as much as 2 million gallons of water per day. And so this 2 million gallons of water can be recycled and reused, but it's used alongside detergents and resins to create that perfect proppant. And again, that perfect proppant is going to help open that shale formation up and make it permeable enough to extract the methane gas. And this water is generally just disposed of into nearby rivers and streams. Here we have a picture of the juxtaposition of freshly mined sand next to that beautiful white frac sand, as you guys can see. So, and not only is frac sand mining water intensive, but hydraulic fracturing is obviously no stranger to water use in and of itself. If we examine that, a single fracking well can use anywhere from 2 to 8 million gallons of water per well. And so when we consider that more than half of all fracking operations in the United States are in areas of drought, and more than 1/3 of all fracking operations are in areas of water depletion, that is to say areas where the total volume of water is being reduced and not recharged at a level that it's being used at, as it would be in the healthy hydrologic cycle. Now, Texas in particular uses the most amount of water in the entire country. They have almost 6,000 wells. So if you do the math, 2 to 8 million gallons times 6,000 wells, that's a lot of water. California particularly, I know some of you may have heard about their recent water restrictions. Well, fracking is actually exempt from all of those, as it may be ironic. Although there has been legislation signed recently by Governor Jerry Brown that will force restrictions on hydraulic fracturing and agribusiness, but not until the year 2040. So I'll be 52 years old to put that in perspective for you. And it's not just about the water use, but it's about what's in it. And so most states consider what's in it a proprietary trade secret, and it doesn't require disclosure. So having said that, the EPA has done its own independent studies, and they have found diesel fuel. Now, diesel fuel is used in mixes to create the perfect viscosity to ensure that those proppants are perfectly placed within the shale to create maximum gas extraction. There's also hydrochloric acid, which is highly caustic. It's often used as a biocide and as a chemical to dissolve limestone and other rocks. There's also benzene. Benzene is highly carcinogenic to human beings. It's often an additive of petrol. And as we've seen about 2 weeks ago now, Pennsylvania specifically found benzene and other fracking-specific chemicals within their own drinking water supply. And so what's remarkable is that only 15 to 50% of the fluid that goes down is actually recovered. What isn't recovered just stays under the ground, chemicals and all. When it is extracted, it's either recycled or disposed of. Now you're probably wondering, how do you dispose of it? Well, we dispose of it in underground injection wells. And really all they're doing is they're digging a well and they're pushing the fluid as deep underground as they possibly can. And so there's an estimated 30 trillion gallons of fracking waste fluid underground. There's around 680,000 injection wells nationwide, of about 220,000 of which have structural failure such as leaks. Now remember, this fluid is injected underground and it's meant there to stay forever. Now there are of course more groundwater concerns. You can see here an open pond, open frac pond, which is used as an intermediate step for fluid that is being returned from the underground to the surface once all the fracking and proppant nestling has occurred. And so when you're dealing with 2 to 8 million gallons of water, there aren't really semi-trucks or tanks that can hold that much water, so they leave it in an open pit. If you can see in the photos, these pits are basically lined with tarpaulin, and for the most part, a lot of them are compromised. And so I really want to turn this on you folks. Imagine that this pit or a spill was next to your house. You can see that this is a direct introduction of these caustic chemicals and carcinogens into your water supply, albeit free of charge. It also has the ability to find its way into nearby surface waters like lakes and rivers, which will then have an effect on fish, birds, and of course other wildlife. One of the other phenomenon is the migration, or as I affectionately refer to it, fugitive natural gas, in which the natural gas can seep up into the freshwater aquifers via natural or existing fractures, and especially through newly created ones, as we've talked about how fracking fractures those rocks and breaks it up. Not just gas, though. Remember, only 15 to 50% of the fracking fluid is recovered, so there's still contaminants well underground. Here's a little bit of a case study from a lady out of Granville Summit, and you can see that the methane gas has migrated into her tap, and as she turns it on and it flows out, she can just light it on fire. Now, two things to really consider. The methane gas, it's almost more immediate, so it'll come and it'll kind of go, but years from now, you know, who knows what's still left behind and is still coming up from underground. So is this going to affect her kids, her grandkids, her great-grandkids? I mean, we don't really know. And so even if we do fracking 100% correctly and we do the best we can, fraccidents still happen. And this is a picture of a blowout caused by a broken wellhead just outside of Fort Collins, Colorado, that allowed green fracking fluid to flow for more than 30 hours. There has been no specific research done to this site. However, as we've seen in Pennsylvania, Ohio, Louisiana, Colorado, fracking-specific chemicals are in our drinking water sources. So how can we do it better? Well, recycle and reuse is really kind of the common theme here. Using recycled water to reduce the need for fresh water is imperative. Now, there's a hydroprod program where the Recycling Corporation will provide on-site fluid waste filtration. That's important because it will reduce the need for underground injection wells. Also, we should maybe rethink or ban injection wells. I mean, at 680,000 wells with 30 trillion gallons of water underground, I mean, how long are we going to keep putting this stuff underground for, right? You can only do it so long. Also, there's a need for more regulation and oversight. You know, why not require the use of non-fresh water as much as possible? Why not have full disclosure of what's going into these chemicals? Also, as I said before, if it's taking California 25 years to put restrictions on it, I mean, knock on wood, but we might not be here by then. And so one thing to note too as well as far as regulation, since 2005, hydraulic fracturing has been exempted from the Clean Water Act. So the irony gets thicker. So let's summarize what we talked about here. Fracking can have possible consequences, especially to water quality and water availability. We can't sacrifice water quality to gain energy independence and superiority. As I've done this project, I can't help but wonder, are we really contributing to the destruction of other people's lives? You know, they can't do this without our frac sand, and so we're directly connected to that. And you know, are we teaching a culture of conservation, and one that's especially connected to nature and water? And so to leave you with something a little more positive, I'd like to talk about what the future may hold. You know, fracking can be the catalyst for energy independence. It can provide energy resources while we continue to create and study and develop more renewable energy. Also, it can teach us a lot about our connection to nature, particularly water, and hopefully it'll help us understand what conservation is really about and why it's so important. So, thank you. And I don't know if I have enough time for acknowledgments, but so I'd specifically like to thank Dr. Tom Neal for allowing me to take on a project of this magnitude, but mostly for teaching me to value every drop of water I drink. I'd like to thank Dr. Melissa Hage for her many crash courses in geology, but mostly for teaching me that it's okay to make mistakes and that that's how we create really solid conclusions. Dale Murray, who I don't believe is here, for taking a lot of time out of his sabbatical to help me and making sure that we know there's a difference between fracking and frac sand mining. I'd like to thank Professor Ald, not only for teaching me to do research, but really showing me what quality research and intellectual development is. And lastly, I'd like to thank Kate Booth for all of her formatting and Bob Onison for his generous time helping me with PowerPoint and all that good stuff. So thanks again.